welcome. Now, those of you who have good memories might remember that at the last third Thursday, I said we weren't going to have one this month. And I apologize for that, but the opportunity presented itself. We got some of our brightest young minds at the College of Engineering who luckily enough were able to present. So we are having one in July, even though it's in the middle of the summer. So we got good stuff for you, and we thank you very much for joining us. Okay. We've been busy, and I guess the big news for us is that we have actually begun scheduling face-to-face training sessions to begin in September, if all goes well. And so after a year and a quarter or so of virtual only deliveries, we will be ramping up. We are ramping up now and heading back towards delivering at least some face-to-face training. We will continue on, obviously, with our virtual training. It's been very successful, reaching a lot of people and getting great reviews and all that. So we will continue that, but it is also very exciting to get back into the classroom, to get our instructors back into the classroom face-to-face with people from across the nation. Okay, so we have a couple of announcements, and for those, I will turn it over to our Executive Director, Dr. Karl Kim. Karl?
Well, it's great to see you all. I hope that you are all staying safe and adjusting to all of the changes that are occurring related to the pandemic and other things that we're working on. Today we have a very interesting set of 2 lectures. We get together every month just to check in, to make sure that everything is good, and then to follow up on some things. We also use this as an opportunity to share good news. And this week we heard that one of our staff members, Rob Porro, was awarded a really prestigious fellowship, the Naus Fellowship, which is part of a nationwide competition done by Sea Grant. And so this is really excellent, great news for Rob. He'll be spending a year either in an executive office or in one of the legislative offices in Congress in Washington, D.C. next year. So join me in congratulating Rob for this really terrific honor. And I'm sure we'll hear more about his plans and experiences. Rob, as you know, directs all of our coastal planning, coastal engineering courses. And so we will have to work to figure out how we're going to do some of these things while he's in DC for the year. But we've learned how to use remote technologies really well. So with that, what I'd like to do is turn it over to Eric Yamashita, who's going to introduce our 2 speakers for today. Eric?
Thanks, Karl. So today we have 2 faculty members from the University of Hawaii Department of Civil and Environmental Engineering. They're both structural engineers. They're both also recipients of our Pacific Southwest Region UTC grant. And so Dr. Karl Kim is also the director of our PSR UTC here at the University of Hawaii. As way of background, the University of Hawaii is a member of this Pacific Southwest Regional UTC, and is composed of USC as the lead institution, plus University of Hawaii, UCLA, UC Irvine, UC Davis, Cal State Long Beach, Northern Arizona University, and Pima Community College. The the UTC is a nationally competitive program funded by the U.S. Department of Transportation, and which advances the state of art in transportation research and technology. And we, as part of this, we try to develop the next generation of transportation professionals as well. The presentations today are from Dr. Chunhee Cho and Dr. DoSoo Moon. I guess we can go to Dr. Cho, if you can bring up your presentation, and then you can start your presentation.
Oh, can you see my screen?
Yes.
Okay, thank you. Thanks for attending my presentation. The title is Bridge Monitoring Pseudo Hybrid Approach, Leveraging a Model Updating Technique and an Artificial Intelligence Method. Yeah, title is quite long. Anyway, so my name is Chunhee Cho, an assistant professor in the Department of Civil and Environmental Engineering. This research is supported by the PSR UTC program. This presentation is my proposal research. So here is outline. The presentation will start with the introduction, then also the proposal method and the sequencer task will be described. Also, the expected research product and contribution to critics will be discussed. The presentation will be ended with a summary and task schedule. As you can see, according to the ASC 2021, our infrastructure, especially the bridge GPA, is a C-. If we want to improve this current status, we need $125 billion. But current spending is only $22.7 billion. No matter how the technology is developed or improved, so we still have the same issues like bridge collapse. So FHWA require the inspection every 2 years, but still has limitations. So like this is just a labor-intensive inspection, so it's a labor-intensive and time-consuming. As you can see, it's unsafe. Also, it's a limited inspection ranges. I mean, our reach is limited. And another issue is that, so if the inspector cannot find the damages at certain inspection, that damage growth will not be detected until next inspection cycle. That's also significant issues. That's why we need a smart structure systems urgently needed to prevent these catastrophes. Okay, this is a basic idea for structural health monitoring approaches. So this is just the brace structure. If we insert the accelerometer, anyway, based on the vibration or environmental load, we can get a response. So in the same structure on the same condition, if the structure has damages, this vibration pattern is changes. Generally, the time period is longer or just the frequency will decreases. So we investigated this pattern, these two patterns, and compared it, and then we back estimated where we have where the structure has damages and how severe it is. We can investigate it. That's the basic idea for the structural health monitoring approaches. So this is actually the pattern, like a vibration pattern, a structural response pattern. So I will use the supervised machine learning. So supervised machine learning is a very good way to distinguish these vibration patterns. But we have another issue. As you know, the machine learning require the high quality data, but we cannot make a data easily. It's kind of difficult to obtain the data on the data like on the damage structures, because we cannot give intentionally give a damage on the structure, right? So we cannot break our bridges. So this is my idea. I just build the model, like acrylic model. The size is 300 millimeter by 300 millimeter, like width and height, and the length is 3 meters. Okay. Then this, I assume that this is a real bridge. Okay. Then I will insert 6 and 8 accelerometers, and then we can measure the vibration, right? Then I build another model. This is a numerical model. We synchronize these two using the model updating technique. So once the model update technique is well done, if we give the excitation, like the same input data, then structural response will be the same. Then we assume that these two are synchronized. In this case, we can give a damage, like we change the member size on the numerical model. That we can emulate or simulate the damage and then generate the damage response. Also, to compare if it's really working or not, we compare this acrylic model. Like we replace the element. For example, we change this element like a small size element, like a smaller section element, and then we also give assign the same sections on the numerical model, and then check whether these two structural responses are matched or not. Once it's matched, then we can generate like a structural response on the damage scenario. So for the data, for the machine learning training, I will use a scalegram. Scalegram has two types of data, including like a time series data and the frequency domain data. So I believe this image includes more information about the structural response. So this is a simple example, like for one structure, like a 6-story structure, we insert the accelerometer, second, fourth, and 6th floors. And then perform the scalegram. As you can see, you show the clear yellow lines, right? Then we give damages on the structure, like on the first floor. Then you can see that there's difference, right? It has another yellow line here. Then we assume that this is based on these 3 images, we can estimate whether damage is located and how severe it is. But this case is very clear, right? But some complicated cases, these two, the images will be different, but the human cannot detect. So that's why I want to use a supervised like a image processing, like a CNN, convolutional neural network. The convolutional neural network is a well-known tool for detecting images. You may heard that some machine learning algorithm can detect the dog and the cat or something like that. So if human cannot detect this small difference, but I believe the machine learning algorithm can detect their all difference, then based on the back estimation, we can measure structures, damages location, including its severities. Okay, this is just a repeat and then brief summary of the proposed method. Like we build a real model. It can be real structure, or in our research, in my research, I build an acrylic model. Then we build a FEM model, like a numerical model, and synchronize these two. Then once we confirm the synchronization, or just make a digital twin, then we just give a damage on the numerical model. Then based on the damage scenario, the numerical model generated a lot of data. So like a structural response. Based on this structural response data, the machine learning algorithm trained. Once we obtain the optimize the machine learning algorithm, then we just give real damages under acrylic structure. Then it generated another structural response. Then check whether this algorithm, like a machine learning algorithm, can detect the structure damages and its severities. This is the main idea of my proposal. Okay, So this is an expected research product and contribution to practice. The proposed methods will continuously monitor structural integrity. That is one strong point. The reason is that current biannual inspection may miss the critical and dangerous damages growth until the next inspection cycles. The second strong point for the practice is that it does not require any additional cost if the sensing system is already installed on the bridge structures, because we just use that sensing system. We just need only data. I believe many of, not so many, but some of the bridge structures already have these sensing systems. Okay, so this is a task schedule. So I just separate the 4 tasks. The first one, we study about the damage scenarios and the structural data. And the second, we update the model to enough reflect the structural behavior of the real model. Then based on the this FEM model, we generate the data and training the algorithm. The task 4 is a validation procedure. Like if our AI model is validated well, or I mean, detect the damage well or not. This is a repeated procedure, like 3 and 4. If the performance is not good, I mean, it's not accepted, then we just go back to the task 3 and to improve the AI model. Also, if the data is not enough, also we can go back to the task 2. So the task 2 and 4 are repeated process. It's an iterative process, I think. Okay. So this is the end of my presentation. Do you have any questions?
That was an excellent presentation. One of my questions that I have is, I didn't quite understand, you're going to construct an actual physical model first and then a simulated model. Could you describe actually, the difference between task 1 and task 2?
Task 1, because we cannot break the real bridge, right? So we use it. So actually, we want to monitor, but we want to get a data, like damaged data. So experiment to propose will build a acrylic model. That's a real model. That's a task 1. And then we also think about the damage scenarios. Like it depends on the structure. So some weak point will be failure first. So we will find the damage scenario. We will describe the damage scenarios. Then we synchronize these 2 models. Like based on the model updating, we want to make a digital twin. Then we give the damages on the numerical model, because we cannot give a damage in the real model. So this is for training the algorithm. So the FEM model generated a lot of data. We can make really a lot of data, or enough data for machine learning training. And then if we believe that this machine learning training is enough, then we just give the real data. So in near situation, we connected these sensors to the machine learning algorithm. But in this research, we want to validate our algorithm is working well or not. So that's why I just build an acrylic model. And then I give a damage to the acrylic model and check whether this algorithm detected the damages and its severities or not. So if performance is not good enough, we will somehow we will find a way to improve our algorithms.
Yeah, it seems very interesting, and I think that there are many potential applications for this. I guess my question had to do with whether this, task 1 was going to be based on an actual bridge. I mean, there have been recent, bridge failures, or a particular type of design that you're looking at, and how actually you go from task 1 to task 2. I think I really understand the tasks 2 and 3, and we've done some work with neural networks and the training process. But I'm interested in the input data and some of in how you're actually going to pull the initial parts of the research together.
Yes. For in this research, I focus on just one specific model. I want to check whether the concept is validated or not, is working well or not. Then for actually this procedure can be applied or generally applied to the other structure. We need to follow the same procedure anyway. Yeah.
Yeah, I'm sure there may be other questions or comments. You can use the chat feature.
Carl, there was one more question.
I think from Goro, right?
Yeah.
Yeah.
Can you train the model to recognize what type vehicle caused the damage or response? I asked as we have many truckway in motion stations near bridges, especially on our freeways like H1, H2, and H3.
So this case is mainly the structural damages. So I haven't categorized the bridge, the failure scenarios yet. So during this project, I will describe the damage scenarios. That can be the answer to your question, or do you ask some other aspect?
No, that's fine. I'm just saying that, we have some very heavy trucks that go over the bridge. They're overweight, and several of, there have been several, we have a lot of old bridges, right? So a lot of these bridges have lower capacities than say modern structures. So I'm just wondering, we monitor all the loads by the axles, and we have pictures of the vehicles. And so I was just wondering if there was a way to train the model to know what is actually causing the response to the accelerometers, right? Because you want to know where the damage is coming from, right? You want to identify it.
Yeah. So no matter, if the heavy truck just goes under the bridge, if the bridge is just okay, it's on the just elastic status, elastic ranges, then maybe the response would not be the changes. The vibration pattern, like the vibration amplitude would be changed, but the vibration, the period would not be changes. So in this case, we assume that is just a stable status. Like the structurally okay, yeah. But once some element shows lose their stiffness, then their vibration pattern, like including their amplitude and also the time period or frequency would be changes together. So in this case, my model can detect it.
Okay, let me give you an example. So our oldest weigh-in motion station is at Sand Island next to the container facility, right? Matson Navigation. Most of our containers comes in. When we were calibrating it once, I noticed, especially heavy trucks at high speed, they would go over the old Bascule Bridge, and that had a metal deck. So as they, at higher speeds, they started to bounce. And as they bounced on the bridge, I could see pieces of the bridge deck break off and fall into the ocean. So I'm just, that was where my question came from.
Okay, so I'm not sure it can detect the bridge deck or not, but if we consider like a global stiffness, I think the bridge deck is kind of quite the minor element. So if it affect the severe like a severities like to the structure, then it can detect, but we just consider the global stiffness first. So if the structure loses the global stiffness, then the machine learning algorithm will detect where the where damage is located. But if it's a very minor assembles, like minor pieces, then may not detect it. Yeah.
I see in the question that Chad has asked a question. He said, figure 4 on the right appears like you can locate where the damage is. Is that the case?
Yes. So this is like a, oops. Yeah. Here, so for example, so if the structural element has damages here or there, then I mean in the real structure, we just keep the damages here and another point here. Like in the acrylic structure, we change the element, like a small sized element that emulate the damages. Then their structural response would be different. Then my trained algorithm will find out the locations, then how severe it is. Like if this element has maybe negative 5% damages, so it's like the stiffness reduction is 50%. Then my algorithm will say this element has a damage with 50% and also locations together. Yeah, these two. So if it has a more, and then it shows a more damages and more severities. Yeah.
Yeah, I see Mary has raised her hand. Mary, do you want to ask your question?
Yes, thank you. My question is how this would benefit first responders. Unfortunately, let's hope there's no disaster, but when there is, how can this speed up the process of finding survivors, victims, areas where maybe there's voids? It seems to me that this might have some benefits to first responders, emergency situations.
Oh, okay. So, like so this system as like an objective to show the whether the damages, whether the structure has damages. Do not think about the first responders. This system, it can be the first responder. So the people find out that the problems, then just this system find out the damages first.
So it can help in terms of preparedness. It can help in terms of mitigation. It can help to sort of prevent the collapse from occurring. But it really isn't designed for, you know, operational. Maybe there might be some rescue aspects of it that might be relevant.
Yeah, I wondered if perhaps the data and the findings from this could come into play if something did happen. That you could generate some information real quickly. That would be vital.
Right.
Yeah.
Right.
Yes.
Yeah.
Yeah. So yeah.
Yeah.
So
certainly, closing the bridge, preventing doing whatever needs to be done to strengthen it, to prevent the collapse from occurring, I think is really critical. It also strikes me that there's so many potential causes that could be. I mean, it could be a design problem. It could be a maintenance problem, as Goro was describing. It could be issues about operations and weight, and then of course there could be events like flooding events or scouring or some other type of action, a collision on the bridge or into the bridge that could cause this. And so being able to think about, you know, the different causes, I think would be really useful as a tool. But I think that there are many possible applications. And what I think is very exciting about this research is the application of AI technologies as well to help with the classification problems as well. we do have a second speaker. So what I want to do is wrap this up. If you have continued questions for Dr. Cho, please put them in the chat box. But I'd like, if we can, move on to our second speaker, although I could spend all day just talking about bridge collapses as well too. So, okay, shall we move along? Thank you very much, Dr. Cho, for your interesting research that you're doing.
Yeah, thank you for your invitation. Yeah.
Yeah.
Okay.
Okay.
Okay. All right, so I think it is my turn. Thank you very much for inviting me today, and thank you everybody for joining today's seminar. My name is DoSoo Moon, and today I will present about the proposed proposals, which is integrate hazard vulnerability assessment and mitigate framework with a mixed reality for transportation infrastructures. So the keyword from the title is vulnerability assessment mitigation framework and the mixed realities. All right, so before getting started, just let me introduce a little bit of myself. So my name is DoSoo Moon, and I got my bachelor and the master degree from the Seoul National University, and then PhD from the UIUC. And then after that, I did some postdoc research at the UIUC at different facilities, so Smart Structure Technology Laboratory and Mid-American Earthquake Center, and Network for the Earthquake Engineering Simulations. And then I joined the Department of the Civil and Environment Engineering in University of Hawaii in 2018, and I'm working as assistant professors. My research interest includes resilience and the sustainable infrastructure under the extreme events, and structure health monitoring using the smart sensing and earthquake engineering. All right, so here is the outline. So I will just start with the research background. So what motivates to do these kinds of research, and what is the issue in the existing method, and then I will introduce what is the proposed approaches, so which can handle all the shortcomings in the existing method, and then I will share what I want to achieve through this project, and then I will wrap up with a tentative schedule. So this project is not started yet officially, I believe. So this is more like introductory presentations. All right, so let's start with the background. So as you can see, we are just, there are many, let's see. Okay, so we have to deal with the many natural and human-made disasters. Okay, so as you can see in this slide, just there was many big events in the previous years. So in 2019, we experienced COVID earthquake, and the 2004 tsunami, and hurricanes in the US in 2005, and the typhoon in Korea, Worldwide Trade Center, and the bombing. So we are experiencing natural and human-made disasters, and then it caused a lot of casualties and economic losses. So, and then as you can see, this event will happen again. So we have to prepare those events. And at the same time, another issue is our infrastructure is aged. So according to the ASCE, so American Society of Civil Engineers, the overall grade for the infrastructure is very low, so D+. So road is a D, bridge is a C+, so all the infrastructure is aging. So without a big event, some a structure can collapse. So as you can see on your right slide. So we have to deal with these two main issues, aging civil infrastructures and also the natural hazards. So what we can do? So what we can do is we can do the hazard risk assessment. So by doing this, we can quantify the risk, and then we can see what is the consequences when the event happens, and what is the best way to mitigate that events. So for this, we need the following three components. The first component is the hazard information. So we have to know about what kinds of hazard we are dealing with. So for example, earthquake hazard map, or tsunami hazard map, or the sea rise a level map. And the second component is we need the inventory data. So what kinds of infrastructure is available at that region. So we can get some building, how many buildings are there and how many bridges are there, how many power plants are there. So with these two informations, and the last component is a vulnerability informations. So basically this shows what is your structural performance under the given hazards. And this curve we call the vulnerability or fragility curve. So basically it shows how well your structure will perform under the given hazards. So among the three components, most important one is a vulnerability curve, because hazard and the inventory is somewhat given. And then what we can do is we can improve these vulnerability components when we do the hazard risk assessment. Then how we can drive this curve. But before just mention that, let's talk about what is the fragility curve a little bit. So fragility curve is a probabilistic indicator of the structural safety against hazard. So we need the following definition. So we have to first define what is a hazard intensity, and then with what is a performance level or damage level. And with these two information, we can draw the fragility curve. As you can see at the bottom figure, and the usually x-axis is a hazard intensity and y-axis is a failure properties. So using this fragility curve is straightforward. So you just find what is the expected level of hazard, and then you just use the curve and read what the failure properties. Then once you got that number multiplied by the number of the inventories in that region, then you can estimate how many buildings, what is the economic losses, so forth. And then this fragility curve is depending on your structure. So depending on if your interest structure is buildings, bridges, or power plant, all this fragility curve will be different. Then how we can drive this curve? So I don't like that. I have to talk about a little bit of the mathematical background. So failure is defined as the following equations. So basically, it just calculates what is the properties when your supply, so S, is less than the demand. So your structure cannot handle your hazard like a load or demand, then we call that is a failure. So there is a two existing method. The first method is analytical function-based method. So basically, this it defined all your S and D term in the random variables, and it drives the mathematical expressions and solve the probability equation mathematically. So it is really complicated and it requires a lot of math skills. So, and then it can be only applied to the very simple structure type. So most of the time, we are using the second approaches, which is a simulation-based method. Maybe you are heard about this method. So one of the represent method is a Monte Carlo simulations. Basically, just like you run the analysis and count how many failed case out of the total trial. So this is very easy method, but it has some problems. One of the problem is expensive computational cost. For example, your failure probability is 1%. That means you will expect 1 out of the 100 cases. But what if our failed probability is less than 1, so 0.01? Then you need at least 1,000 simulation to get at least 1 failed cases. So depending on your failure target failure properties, it suffer from the computational cost. So because of these issues, like this project proposed another approaches. So that is the following slide. So here, instead of the evaluate S and D at the same time, it evaluates supply and demand separately. So what it can do is like it estimate the response, the demand by the Monte Carlo simulation approaches. But when you calculate the failure probability, it uses a math skill. So it can just get the more accurate failure properties. So for that technique, we will use a form. So I will explain a little bit in the following slide. But for this one, we have to couple the structural analysis and relative analysis softwares. But by doing that, you can get the more accurate and more efficient. That is a keyword. So you can just like get the fringe curve very quickly. And also because of it has like a less computational cost, you can use a more detailed analytical model. So your estimation will be more accurate or more realistic. Okay, so this is a proposed structural reliability analysis platform. So first, we identify the uncertainty in your materials or structures or load. Then using that information, we can do the structural analysis and reliability analysis. But here, like unlike the previous approaches, these two different software can talk each other and exchange the data, so they can just calculate the failure property mathematically. So using this one, you can just calculate the fragile curve. So in order to just do this all analysis very quickly, we adopted the FOAM approaches. So FOAM stands for the first order reliability method. So as you can see in your left plot, the orange line is a failure domain. So that is the original space. What we do is we transform to the standard normal spaces. And then after that, we approximate the failure domain with a linear line. Then we can easily estimate what is the most probable point. And then using that information, we can estimate what is the failure properties. So using this technique, when you compare with this proposed method with the Monte Carlo simulation, you can see this is a very efficient and accurate. So in these cases, our target failure probability is 2%. But as you can see, the red is a Monte Carlo simulation, and the blue is a proposed method. And x-axis is a number of simulation, and the y-axis is failure properties. So our proposed method, we can get the target failure properties within 21 simulations. But as you can see, Monte Carlo simulation, more than 1,000, still it is not converged. And it requires a lot of analysis. So it just shows the proposed method is more efficient and more accurate. And this is like another simulation result. So in this case, I just study the 3D building structures, and then I just try to drive this frigid curves. All the figures, the dot is simulations. If you are using the Monte Carlo simulation, this dot, it requires 1,000 or several thousand simulations. So getting this curve is it takes a lot of time. But when you compare with our approach with this Monte Carlo simulations, so this is a comparison. So when I use a Monte Carlo simulation technique with a supercomputer, and I use only 2D models, still it takes 456 hours. But proposed method, I use a simple my personal computer, and then I use a 3D model. So each simulation will take more time, but still I can get all this curve within 36 hours, so within 2 days. So this method is very efficient. Okay. So yeah, so then using this framework, what I want to do is, let's say we have workers, and workers just go to the breach site and inspect the damages. When the damage is found, what they can do is they report where is the damage is. Then this damage information can be update our numerical model, and it will show what is a change in your fragility curve. So as you can see the light figures, if damage happens, your failure property can be changed. So your curve can be shifted one. So using this integrated framework, your damage information can be easily integrated, and more up-to-date fragility curve can be obtained. And another thing I want to touch from this project is, because all the practitioners, they will inspect the breaches. So just reading this plot is not easy. So what I want to do is I want to use virtual realities. So I want to use a Microsoft HoloLens, and then it can just visualize a 3D plot of the breaches, and it indicates where the damage is. And then if we just select, this is a damage point, and then it will show what is change of the your freeze curve. And also the table, what is the expected consequences. So what is the your level of the economic losses when the certain event happens. So it will be very useful. For example, if you have only limited resources, then you have to optimize like where you want to use that resources. Then just you can just like select several damage point and see the what is the consequences. Then you can easily prioritize which damage is most important. Then you can optimize your resources. Okay, so that is this project object. So the goal of this project is advance the integrated vulnerability assessment platform, and then using that platform, assess the coastal hazard vulnerability of the transportation bridge structures with the damage data. And then the final goal is create the 3D virtual reality models and explore the data visualization in the mixed reality using the Microsoft HoloLens. So simple two word is like through this project, I wanna do the better risk assessment, and I wanna just like give the better visualizations. Okay, this slide showed what is a tentative schedule. So first phase is conduct the literature review, and second phase is advance the integrated risk assessment framework. And the following phase is develop the progressive risk analysis with the damage data. So we will use the damage data and update our model and then do the risk assessment. And the fourth phase is create the 3D virtual reality models and develop the argument visualizations. And the final phase will be the wrap up all the findings and write the report. So there is a tentative schedule, and it is I think it is a 1 year project. Okay, so that's what I prepared today. So that's it, and thank you very much. And if you have any question, please ask me. Thanks.
Yeah, thank you for your presentation, and I really liked your clear explanation and the background on the research. It strikes me that there are going to be some types of structures and some types of damage that might be more readily detected than others. I'm wondering if you can talk a little bit about the types of damage that can be detected and then simulated with this approach. I think that there's some, with especially in the built environment with structures, there are more uniform surfaces.
Mm-hmm.
What about places where there's more spatial variation, or it might be more challenging. But anyway, I'm just curious about the types of damage that you're going to focus on.
So basically, just I will focus on the structural damage. So which can just affect your structural performance. So, but when the practitioner they do the inspect the bridges, they will report the damage locations, the crack size, all the details. I can just implement all the damage information to the model, and then it can just show what is the consequences from the damages. So it can include all kinds of damages. Yes.
Mm-hmm, mm-hmm.
Mm-hmm.
Well, let me open it up. And are there other questions or comments about either the presentation or the methods or the applications from this? Any questions or comments?
There was an earlier question in response to Dr. Cho's presentation from Chad that we missed. And Chad is asking, do the response graphs vary based on type of loading, specifically seismic, wind, live, etc.?
Okay, so based on so it can be all kind of the loading all kind of loadings, but I'm focused under just environmental the vibration first, like your after just our schedule, we figured out anyway the structure will have damages. Some structure would be fine, but we are just want to monitor the current status if it's okay or not. So because the structure damages are just gradually developed. So that's why I consider all types of the loadings, but especially I consider more just the current, just general cases like a dead road and live road and wind road. Yeah. So it's another some the harsh conditions like earthquake load or typhoons. Yeah. So just consider general case because of the structure damages that's gradually developed with some reasons. Yeah.
Okay, great, thanks. And there's another question here that I guess is a follow-up to that from Jeho. Is physical model made with different material, non-acrylic, would affect the vibration model?
Yeah, it should be because of the stiffness changes or physical properties changes. So the vibration pattern and damage pattern would be changes. So in this case, we need to make another like a numerical model and then synchronize it, and also need to train the machine learning algorithm again.
Yeah, I'm sure you've thought about this, but given all of the problems that we've had with building our elevated rail system, it's not just the track wheel interfaces, but also some of the concerns about the structures, trying to think about, different applications and uses for these technologies, these sensing systems, I think would be really useful. Again, keep bearing in mind that there are so many different underlying causes, from the design, from the operations, from changing from 2-car trains to 4-car heavier trains, other types of factors that enter into this, and not the least of which are the actual construction practices and whether things were whether they were built according to specification and so forth. So, but very, very interesting and I think important research. We had a comment or question from Erica. Erica, do you want to come on? Great to see you, Erica. You're coming in from Australia, aren't you?
Yes.
Yeah.
Hi, Karl. Nice
Yeah.
to see you. Thank you for your presentation, Dr. Moon. I was just very curious about your visualizations. I think that was a really interesting piece. Can you describe a bit more about what the visualizations will show? I mean, will it point out locations where damage may occur or actually display consequences? And it seems like it could get quite complicated. That's why I asked. And then also the users of the visualizations. I was curious about that too. But thank you for your presentation.
Sure. Yeah. Yes. So it is combined. So your visualization. So first, you can see the 3D version of your physical model, and then you can see the location of damages. Then when you just click the damage, then you can see what is the consequence of the damages compared to the current one. So either show the graph and the tables and the location of the damage, everything. And then the practitioner, they can just use this HoloLens or the decision maker. They can just use this one, and then they can easily understand what is the meaning of the engineering findings. Because usually decision maker does not know what is the means of these plots. So what I want to show is I visualize all the kind of result, so they can easily understand what is the consequences. So which damage is most important, so which damage is less important. Such things. Yeah.
Thank you.
Yeah. Thank you.
I see a comment from Chad. Chad, do you want to come on and share your idea?
Well, I was just thinking if you're analyzing existing structures and you're looking at, you know, an acceptable level of failures, and realize that, events could be more likely in the future, then you could adjust your building codes such that to bring your failure probabilities into an acceptable range. That's all.
Mhm. Sure. So one of the ideas, maybe it'll be just follow after this project, but this one is a focus on one events. Well, some events will happen at the same time. For example, tsunami is following after the earthquake, but current design code does not really consider those effects. They just only provide the design code only for the earthquake engineering or earthquake or for the tsunami. But yeah, this framework can be used when we have a multiple hazard. So what will be the consequences? Yes, so yeah, it can be just used for the building code update. Yeah, thank you.
Yeah, I do like that idea of connecting this research to building codes and other types of actions that we can take to increase the safety and security. Are there other comments or thoughts?
Junath has a question here. Junath, you want to chime in?
Yes, sure. Thank you. Thank you. It is very helpful presentation. Thank you to both presenters. We are also doing kind of some machine learning work, and data has been always the challenge, especially doing more innovative kind of work. So I was wondering how the data part are being dealt in your models compared to other conventional kind of approaches. Amount of data and accessing data, formatting data, and all that.
Do you ask me or Dr. Moon?
Yeah, Dr. Cho and Moon, if possible.
Okay. So the current machine learning, the approach for the structural health monitoring, because we cannot get enough data. So then machine learning detect only the failure or just okay. Because we cannot get the collapsed data. So so the machine learning algorithm just say that this Bible pattern is okay. So the structure would be fine. But once they detected some sudden data types, so data patterns, then the machine learning algorithm said, oh, the structure has some problem, but they don't know what problem, what the severities. So they cannot find out the damage locations and damage severities. But my approach generated data like a damaged scenario using the FEM. Then the machine learning algorithm can train the damaged case. So that's why my approach can detect the damage location, including the damage severities. That's a big difference. Okay.
Thank you.
Yeah, thank you.
Let me chime in here. So what Junat's talking about is somewhat when we're training our models, or we're doing more object detection. So we need a lot of pictures or whatever to train the model. And that takes time in with your computing and all that. And so I saw Dr. Robertson's on too, right? He deals with that STEER program. So I was thinking, with some of the images they've taken with, whether it's with 360 imaging or other, they have a library of damage photos and other things. Can that be used? I guess for specific things, if a damage to a building or something, you could try to train your models to use that imagery to to help, I guess, make your predictions more accurate.
Yeah, so do you mean the damages, the data, I mean, images is just like
Yeah,
photos?
Yeah, to locate what structurally failed or something from these images.
That I think that would be some another approaches. Actually, my approach is based on the structure vibration. So also structure has damages, the vibration pattern is changes. So we don't know we can diagnose the pattern directly. So I just need a help from the machine learning algorithm. The machine learning algorithm can detect can distinguish the vibration patterns. But your case, you use the figures like crack photos from the structure, right? So in this case, I think we need to make another paradigm, another concept of the damage detections. That can be also quite, I think, the interesting topic for the research. But so I need to think about the more to integrate your suggestion to my system. Yeah.
I can chime in, Ian here. I heard my name, so I got to chime in. But yes, the pictures gathered by Steer are all going into Design Safe database, along with thousands, many hundreds of thousands of others. So there are efforts. I know the Sim Center at Berkeley and other facilities are looking at developing ways to detect that damage from imagery. It's very difficult. I think Chunhee has picked up on something that is a little easier to do, because he can generate, in his numerical model, he can generate thousands, hundreds of thousands of simulations very quickly to get different damage states. He can damage this or that or that or that. He can just randomly create damage and get all of these damage states. And then he's just comparing a vibration of the real structure with this catalog of images or records. And just by finding the difference between the two, you can tell which one is closest. And then you check to see if that is in fact the right image of the damage. So it's quite a different thing than trying to look at photographs and detect a crack, which depends on how close you are to the crack. You know, some cracks look big, some cracks look small. It depends where the camera is relative to the crack. You can't a priori tell the size of the crack even from the photograph. I don't know how they hope to do that, but yes, people are trying. Some areas where they've succeeded is determining the amount of roof damage on a building from aerial photographs or street view camera. You can tell what's undamaged and damaged to some extent, but if it's an old roof and it's got some coloring on it and it's got debris on it, they get confused. So that's a more. I actually think Chunhee's onto something that's a little more manageable.
Yeah, that's really interesting. It's also whether you're doing kind of before after assessment, where there's some really change, and we've been a bit more successful with things like utility poles or power lines, maybe some roadway features. But the question is, can you do it without, so that you're actually training it to recognize certain types of damage and levels of damage. I mean, the other thing, obviously, that we've been working on and struggling with is just using the same cameras, the same techniques, the classifications to determine whether or not pedestrians are masked or unmasked, wearing face coverings, right? It's kind of like, is that a cookie or a dog's face, right? Classification problem. I mean, because a lot of times it's like a human can make those classifications and determine really quickly, but sometimes trying to train the machine is really challenging. And so I think this is a really exciting, interesting area of research. I think it's really fortunate that we have these researchers who have joined the university. I am really keen on more collaboration and more ways that we can bring the engineering and planning and design communities, but also the emergency managers and people that have to think about what are we going to do about this in terms of risk management and also in terms of hazard mitigation. So I think we're at an hour and a half. And so I'd like to thank our two great speakers for today. Encourage you all to interact with us. We can stay on and for a little bit more informal conversation. But again, thanks again. And we really look forward to working with you with the UTC and with the NDPTC and our Pacific Urban Resilience Lab efforts. So thank you all very much for joining us. Thank you. Yeah, congratulations, Rob.
Thank you, Carl. Appreciate that. It's going to be a bit of a shock to move to DC in January, but I think it'll be a good experience.